Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 35. We were talking about the chip thickness ratio, and in context of that we had derived out this formulation related to the ratio of T1 and T2, T1 being the uncut chip thickness and T2 being the cut chip thickness, and it basically resulted in the angular ratio sin phi by cos phi minus alpha. And this is a very important term, the cutting ratio, because that determines a lot of properties to the chipping process, and it also determines how smooth would be the surface finish based on the different velocities and the depth of cut and the cutting ratio, all these terms together. So let us now do a little bit of mathematical conversion here. We already had sin phi divided by cos of phi minus alpha equal to r, and from that formulation we can always have sin phi as r cos phi cos alpha minus r plus r sin phi sin alpha. I am just expanding the cos phi minus alpha term here, and then we do some rearranging and try to get all the sin phi's together. So I have 1 minus r sin alpha whole bracket sin phi on one side, and that becomes equal to r cos phi cos alpha, and so from that I can easily have tan phi, which is sin by cos phi, as r cos alpha divided by 1 minus r sin alpha. Okay. So we have a deterministic formulation for determining the shear angle phi, and basically phi would really depend on what is the r and what is the alpha, that is how the tool makes an angle with respect to the vertical, or the break face of the tool makes an angle with respect to the vertical in any cutting process. So having said that, now we want to just further take one geometrical estimate of what is going to be the shear strain which is involved in this chipping process. So for that, let us actually just draw this chipping formulation process again. Let us say this is the chipping action which is happening, and owing to that there is a shear angle which has been formulated. Okay, let this angle phi be there with respect to the workpiece surface, and we have the extension of the workpiece surface. So this right here is the rake angle and phi, and this is the remaining portion of the cut surface. This right here is the tool. So we are making a clearance angle on the tool on one side and the rake angle on the other side. So having said that, now we want to really find out what is going to be the state, the total shear strain that is needed to do this de-chipping action, or the chipping action that is going to take place. So let us call this point S as usual, and what we do here is this is the work. Okay, this is the direction of motion of the work V. This point we call O, and what we are now interested in is to sort of draw a line which is parallel to the shear plane. Okay, this is the shear plane. So we draw a line parallel to the shear plane, in a way so that the angle that this line makes with respect to the finished workpiece is also the same phi. Okay. And then we consider a triangle by putting a, and we call this point A, okay, and the point which is obtained by just projecting the point S forward and the intersection with the line that we have just drawn here as the point B, and the point which is corresponding to the tool chip interface here with the intersection of the dotted line that we have just drawn as the point K. Okay. So, this point is K. So, if we were to actually drop a perpendicular from the point O on the surface AK, let us call that perpendicular here connected to the dotted line as the point N. We have a case here where the total amount of deformation that would otherwise happen to a surface because of the cutting action can be easily recorded. Okay. So, if we just look at a magnified view of this particular region right here, let us draw this region somewhere here in a call out. Okay. So, we have now a line which is perpendicular at the point O, where with respect to that you define the rake angle. So, this line with a line OA, okay, which is corresponding to this flank of the triangle that has been illustrated, and then a point K here somewhere here, which is corresponding to the point where the line parallel to the shear plane has cut the tool chip interface, and then a line joining the points A and K. Obviously, the angle here of this line along the AB direction, part of it, segment of it AK, is at an angle phi with respect to the finished workpiece, and you have a perpendicular dropped from O all the way to the point AK, okay, and this we call as N. So, if I consider the initial thickness of the chip to be delta, let us say the thickness is defined here, for example, this particular thickness is delta, and we want to find out what is really the deformation which has happened onto the chip. So, I would say that the presence of the tool makes the chip change from orientation OSBA to the orientation, if I call this let us say S prime, OSS dash K. So, basically the chip present is like this, it is like this parallelepiped that you can look at it. Okay. So, this is this parallelepiped OSBA all the way here, and this chip is being deformed because of the chipping action or the chipping process, because of which the next element which happens here is OK S dash S. So, the total amount of shear strain, the magnitude of the shear strain would actually be equal to gamma is the total displacement that has happened to this element moving from OABS to OKS dash S. Okay. That is total displacement is AK divided by the initial thickness delta. So, that is how you define the shear strains, and in this particular case the AK can again be split up into two parts, AN plus NK, and the total shear strains magnitude would be AN plus NK by delta. And now, let us actually see what are the different values. For example, what is going to be AN by delta and what is going to be NK by delta. Okay. And so, for doing that we just geometrically try to estimate the angle OKA. So, the angle OAK is actually this angle right about here, and if we consider that to be some value, let us say theta, then obviously in the triangle NOK the angle NOK should be equal to 90 minus theta. So, you have a case here that you have an angle 90 minus theta here, which you are adding to 90 minus phi and to alpha, and the together the sum is actually one right angle, which is demonstrated by this O A O, and let us call this some value q. Okay. So, A O q. So, then from that the theta can be expressed in terms of phi and alpha. So, theta here for example would be 90 minus of phi minus alpha, and if I were to just explore what is the value A n by delta. So, A n by delta, and delta is basically O n. You are aware that that is how the O n was drawn here as a perpendicular. So, it is basically the thickness of the undeformed chip, you can say, and so this O n value becomes equal to delta and A n by O n. So, basically this is nothing but A n by O n, and A n by O n is actually tan of 90 minus phi, which can be recorded as cot phi. Okay. So, this is tan of 90 minus phi plus n k by O n, and n k over O n is basically again tan of 90 minus theta. So, you have this as tan of 90 minus 90 plus phi minus alpha, which is actually the value of theta, and so therefore, I just continue here, the value of the shear strain gamma is actually equal to cot of phi plus tan of phi minus alpha. Okay. So, just by knowing the angles now, which is phi and alpha, you should be able to predict what is going to be the value of the magnitude of the shear strain which is generated for the chipping process to happen. Again, as a recall, we are just assuming the initial thickness of the chip to be this delta, which is actually although the chip is a parallelepiped, but the thickness which actually is the initial thickness is the delta value, and you are actually subjecting the chip to shear, so that it moves along the distance A k, and from a horizontal orientation it goes like this. So, there is some kind of a shear deformation which happens, and that is what we are trying to gauge by looking at the magnitude of the shear strain. And shear strain obviously is the perpendicular deformation per unit the thickness of the material. So, let us do a numerical problem now. Coming back to this problem here, during an orthogonal machining operation with a cutting tool having a rake angle of 10 degrees, the chip thickness is measured to be 0.4 mm, the uncut thickness being 0.15 mm. We have to determine the shear plane angle and also the magnitude of the shear strain. So, the first thing that we have to do is to determine what is the R, the thickness ratio, which is actually T1 by T2, as we can see earlier. So, this is actually the uncut chip thickness by the cut chip thickness 0.15 by 0.40. So, obviously, the thickness changes because of the shear deformation process. So, this comes out to be equal to 0.38, and from the R and the given value of the rake angle alpha, we could calculate the phi, and so we have phi as the tan inverse of R cos of alpha divided by 1 minus R sin of alpha, alpha being 10 degrees. So, this comes out to be 21.8 degrees, and from that you could further record what is the magnitude of the shear strain gamma, which is actually cot of just in the last step we have formulated phi plus tan of phi minus alpha. So, this comes out to be equal to cot of 21.8 degrees plus tan of 21.8 degrees minus 10 degrees, which is equal to 2.5 plus 0.21 or 2.71. So, that is how you calculate the gamma value and the R value and also the phi value in this problem example. So, having said that, this kind of brings us to the end of this particular module, but in the next module, so we have now figured out what is the geometrical relationship between the various dimensions as well as angles that the tooling formulates with respect to the surface where the chipping action is taking place. The other thing that I would like to point out now is what are the interplay of the forces, or what are the relationship between the various forces that are involved, and then finally try to do something on energy minimization, so that we can estimate how the shear plane gets formulated by different cutting criteria. So, having said that, I am going to end this module here and look forward to seeing you in the next module. Thank you so much. Bye.